Thank you for the introduction. My talk today is a little different to some of the other talks that we've heard, but all the new technology that's coming into the market is basically driving more work for the engineers. So what we're going to look at here is how can we do that work in a more efficient way? How can we drive some of the engineering activity further upstream into the development process? So first I'm going to give a little introduction on the methodology or the challenges, then give an example of the complexity of an engine application in the non-road space. I'll talk about the model-based calibration approach that we've adopted at AVL and give you some use cases. And this is where it ties into some of the previous speakers, where some of the use cases can help to identify some of the emissions challenges, and whether that's NTE testing or virtual PEMS testing. So a non-road engine, what are the drivers for this market? So you have the legislation that defines test cycles. You have, in future, as we've heard, the requirements to do PEMS testing, field testing. We've got the challenges of balancing cost of ownership, which is a mix between the purchase cost and the operation cost and the service and maintenance cost. And these engines have a broad application matrix. So this drives very complex systems, as we've heard, DPF, DOC, SCR, EGR, all these different technologies, and they're all being applied in slightly different ways across the field. So to take an example, so if you looked at a typical non-road 120 kilowatt four-cylinder diesel engine that most manufacturers produce, that engine will have applications in agriculture, it'll have applications in construction, you may see gensets that have been spun off of that platform, and you may even see marine engines. All of those applications have very different and unique usage profiles. And to develop those engines, not only will you have different usage profiles, they'll actually have some hardware differences. So you'll see differences in sub-ratings. So you may have one engine that goes into an excavator, but there'll be 3 different sub-ratings for that application. As well as that, you'll have hardware variation. So you'll see different after-treatment system layouts, you'll see different intake systems, and the actual engine itself, different PTO options, for example. So it's not unusual for one engine to see over 200 different applications that the engineers need to work with. In addition, once the engineers have developed that product, they have to de-tier that engine to be used in other markets. So you then need to develop multiple applications where you're varying more significant hardware components, whether that's fuel system, air system, or after treatment. So how can we help in that way? If you look at the traditional V-cycle process that's used to develop engines, you start by defining the user needs and go through a requirements and design exercise and through to validation on the other end. The approach that we've adopted is to apply model-based technologies throughout the whole process, and to do that in parallel with the conventional development process. Some of the key lessons or learning that we've had from this is that you have to introduce the models very early into the life cycle of the product. You need to use those to help develop your system requirements. So what does the system architecture need to look like? You can do that in a model space, right the way through to your system validation. And at each stage, you need to make sure you're using the right level, refinement, accuracy of model for the purpose that you're using it for. It's not a one-size-fits-all approach. So the example that I highlight here is that if you're trying to do an upfront requirements capture, what does the after-treatment system on this engine need to look like? You don't need a fully predictive engine emissions model. But if you're doing validation work or you're doing pre-calibration for diagnostics, then you probably do. So it's being aware of what tool, technique, process to apply at the right time. The modeling approach that we've taken is a semi-physical approach. So this is a combination of physical engine models and empirical data. And we look at the engine and the aftertreatment as different subsystems and apply the appropriate methodology in each area. What we're really trying to drive for here is to develop models that can run at a very fast rate to work in a hill environment where we're using the models tied together with an engine ECU, so we get real-time feedback. And in order to do that, you need to make some simplifications in some area. So the key here is understanding the trade-off when you make those simplifications. So just to dig into that in a little more detail. On the engine side, as I mentioned, we have this semi-physical zero-dimensional approach, as opposed to a full crank angle resolved one-dimensional engine modeling approach that everybody does, including us. But in this instance, we're applying this in the appropriate way because it's needed for fast-running engine models. But we're still calculating a lot of the engine data in a physics space, so it's a combination approach. One of the outputs of this approach is that we can be predictive in our NOx estimation. So when you're doing calculations on how would the engine respond to a different set of environmental conditions, you need to be able to reliably predict that response, not only in the base thermodynamic outputs of exhaust temperatures and flows, but also how does the combustion change under those circumstances. On the aftertreatment side, we basically build up the models with the components as you'd see them, having a combination of thermodynamic models and kinetic models so that we can represent the chemistry of the system as well as the warm-up profile. On the vehicle side, again, depending on where you are in that development chain, you can apply a very simplistic vehicle model, or you can apply a very detailed model that includes the full drivetrain transmission. And when you're running in the virtual environment, you need a control unit to control the model. So the engine model needs to respond to inputs of what EGR set point to be at, what timing set point to be at, and those in a real ECU, you derive at those outputs via a series of complex algorithms. So we need to incorporate those complex algorithms into our modeling environment. And we do that with a software control unit. As an overview of this is how our modeling environment would look. So you can input the drive cycles. These could be legislation cycles or real cycles or data collected from the field, and you can replay that back through the system. When you put that information into this modeling system, the model ECU takes those inputs in the same way as an engine ECU would, and then drives the engine actuators, which can be modeled or real, and feeds those into the engine and aftertreatment models that then feeds the output back to sensors, virtual sensors, and then back through to the ECU for closed-loop control functions. And the output of that exercise is the engine system response. So you'll get the torque output, you'll get the temperatures, flows, pressures, as well as the emissions key emissions for NOx and CO2. PM prediction is always a bit of a challenge in a modeling environment. So as a initial level modeling, we can get indications, but it requires a lot of engine data to get high refinement in modeling the soot prediction. So the next step beyond the virtual, the purely software base is we go to our virtual test bed. Oops, can I get back? So within the virtual testbed environment, The challenge for the calibrator is, I guess for people in the development community would understand that calibrators like hardware. They want to go and sit in a vehicle. They want to get their laptop out and actually make changes and see the results. So the challenge we had is how to get our calibrators into this virtual concept. So we try to reproduce the same operating environment that they would see if they went to an engine testbed environment. So we have these virtual test stands where the model, the engine after treatment powertrain model is built into the system. The model is controlled by a testbed control system in exactly the same way it would be in an engine dyno, and you can then control the operation of the engine via DOE tools. So the calibrator that's used to going down to the engine test bed, he has his DOE that he runs, he has a test script, a validation test. It's the same test that they run, and the output data is the same data, it looks the same, and they post-process and analyze that data in the same way. So it allows them to be more efficient. It also gets over some of the natural resistance you get in getting the engine development guys to work in this virtual environment. So some of the use cases that we've applied for this, so the list I won't go through in detail, but I'm going to touch on some of these examples now. So first of all, optimizing for non-standard conditions. So this is an example that we went through. This is a 2 litre per cylinder engine, and in this case we're looking at how do you optimize the torque curve of that engine at different altitudes effectively. How do you find the best combination of set points, whether that's EGR, VGT, throttle position, etc. The approach that we've taken is using this virtual environment. We can run all the different conditions in the virtual environment, vary the atmospheric pressure, vary the temperatures, and using the DOE tools, as I mentioned before, the same tools that you'd have if you were on an engine test bed. The model would run at all of those different conditions, generate a mass of data. You're then using a DOE environment to post-process that and find your optimal set point. And in the example that we're showing here, we started with a customer calibration at sea level conditions and their calibration that they'd derived in traditional methods at altitude. We run through this optimization process in the virtual world and develop a new optimal set point. And in this case, that was able to provide them a torque increase on their engine. This methodology, again, it's a modeling simulation environment, so it always needs validation in the hardware, but what it does is eliminates a lot of the guessing that happens during that process. So we've talked about in-use testing. Once you've built the modeling environment and once you've used engine data to enhance the accuracy of the model to the point where you can be reliable on your emissions prediction, then you can start to do some of the things that we've been talking about earlier in a virtual environment. So you can run virtual PEMS testing. You can operate at different drive cycles, ambient conditions. You can feed that into the system, and you can run the same reports that you'd see if you went and ran the PEMS testing on your application. And this is a key enabler for helping you to screen some of the issues that may pop up once you get to the testing, but by that point it's too late. Another use case that we've had is multi-variant calibration. So as I mentioned at the beginning, you will see one engine being spun off into lots of different variants. That takes time. If you have to physically build the 200 different calibrations for that engine and validate those on an engine, that takes a lot of time. With this methodology, you can shortcut some of those challenges. So you can apply different exhaust lengths and you can check or calibrate for the differences. Let's skip through some of these. Another use case that was talked about early in a presentation yesterday is in the future, key challenges are catalyst light-off for low NOx. So because you have a catalyst model that is thermally predictive, you can use this approach to do some of those trade-offs. You can try to seek that optimal balance between getting the right thermal energy into the after-treatment to get to the light-off point versus the fuel consumption trade-offs by varying all the parameters. And once you've done that down selection screening process, your engine testing portion becomes quicker. You can also evaluate multiple different configurations very quickly. Another aspect, a use case that we've been looking at is robustness variations. So if we talk about, yesterday we talked about the 0.02 NOx challenge, and in a laboratory condition that seems plausible. But what happens when you start to introduce some of the variation and noise factors that you see in the market? So, small changes in boundary conditions as well as tolerancing differences on the sensors and actuators. With this approach, you can run a DOE methodology to add in all of those variation parameters and understand what the key parameters are that are driving the output. You can look at what is your production spread of a NOx sensor output. You can feed that into the system and see how that translates to what does that do to your NOx emissions at the tailpipe under these type of driving conditions, and screen some of the issues that may come up later. And again, this is an example that we've looked at where we run through that DOE process. So we would understand what all the possible variations would be, build it into a design of experiment that we run in the virtual space, and then use a statistical approach to highlight where the key concerns may be. Just a nice picture of our virtual test field. This is actually our test field in Graz in Austria. So we have something like a dozen of these set up now that are running programs. And this could be pre-calibration, looking at getting both in the on-road and in off-road, so pre-calibration of the base mapping, but as well as pre-calibration for diagnostic monitors. You can get to an 80% calibration very quickly in this environment before you then start including hardware in the process. So as a summary, application variant proliferation will continue. We've talked about the regulations continuing to drive us forward in the right direction, but by doing that we're adding more variants into the mix. Some of the key lesson from us is that model-based development should be introduced very early into the development process so that you can maximize the benefits. It's not a separate tool, it's something that needs to be fully integrated into your development process to see the benefits. And you need to apply the appropriate accuracy for the appropriate use case. Most of the manufacturers have very good 1D engine models that are used within their simulation environments, and they're very good at helping them to optimize their engines. But that isn't necessarily the full level that's needed for different parts of the process. So it's where do you apply the appropriate modeling technology as a key. And as a final point, if you adopt this approach, you can reduce some of your field testing and validation, but it's never going to eliminate it. And we've run multiple programs with OEMs with this approach, and they've realized a real benefit, but some of the side benefits are they find issues earlier. When you develop your development test plan, you don't plan for failure, but everybody finds finds issues in the process that delay the result. So by adopting this methodology, you can try to catch some of those things earlier. So that concludes my presentation. Thank you.